Hello students, welcome to the online class on solid state physics, which is of paper 6A in your semester 5, which is an elective one in physics. I am N. Chandana, Assistant Professor of Physics from Government Degree College, Khairtabad. So let us learn the basics of solid state physics today. So, in your basic classes, in your primary classes, we have learned what is matter, right? Matter is made up of atoms and molecules. So any matter comprises of atoms and molecules in different arrangements. So matter can be existing in three states, right? There are solid state, liquid state, and gaseous state. Now we are dealing with solid state physics, so we have to learn what are solids now. So let us see, you know that solids are more denser than liquids, and liquids are more denser than gases. Denser means density. So the density solids is more than liquids and liquids is more than gases. So let us go to solids. So we know that some solids are very much brittle. That means they're easily breakable. And some solids are ductile, some are malleable, some are strong, some are weak. And some are good conductors of heat and electricity, and some are magnetic, some are non-magnetic. You know that. See, good conductors of electricity. Let us see this point. See, whenever we connect a battery to a copper wire, so the current passes through the wire. So the material copper is a conductor then, because it is allowing the current to pass through it. But when we go for other material, for example, a wooden block, you connect a battery to a wooden block, will that allow current to pass through it? No. Yes. So obviously it doesn't allow. That means it's a insulator. So we can say that some solids are good conductors, some are insulators, some are bad conductors, some exhibit thermal conductivity very well, some exhibit electrical conductivity. Similarly, some are more resistible and some are less resistible, and some are magnetic, some are non. You know ferromagnetic substances, paramagnetic, diamagnetic substances, antiferro, antiferri. See, these many materials are there under solids. So now let us see the other concepts of solids. So they are primarily classified into amorphous and crystalline materials. So crystalline material means where atoms or molecules are regularly arranged, or they are arranged in periodic manner. They are called crystalline materials. While the materials in which the atoms or molecules are randomly arranged, such type of materials are called amorphous materials. So here they are shown here. See, in crystalline materials, see they are equidistant. The materials are arranged in a series of arrangement. And while here you see they are randomly arranged. That means here one molecule is here, other molecule is somewhere else, in that fashion. So they are called amorphous material. For example, amorphous materials, for example, is what is that? Silica or glass material. While for crystalline material, we have sodium chloride, potassium chloride, cesium chloride. You have various types of crystals. We will watch them in the next classes. Okay. So let us see in detail now. So a crystal. What is a crystal? It's a solid composed of periodic array of atoms, as I've told earlier. And what does this study of solid state physics aim? Studying of the solid state physics aim at macroscopic properties of material of a solid with the microscopic particle structure. Okay, the arrangement of microscopic particle structure, we can easily depict the macroscopic properties of the materials. So in that, how do we estimate the structure of a material? So now the question comes in your mind, like how do you determine the structure of any crystalline material? How come you can do that? See, you have been under an accident and your hand got a little bit fractured. So immediately you'll be advised to go to a doctor, like the orthopedic. So there, the orthopedic, what does he do? So he'll immediately write an X-ray to you. Okay. So X-ray to your hand. So then you'll go for an X-ray. Then what you'll do there? So immediately you'll undergo that X-ray. you'll put your hand near the X-ray machine. So X-rays will be allowed to pass through your hand and the spectrum will be analyzed and you will get a handful of X-ray in your hand. So you'll take that X-ray to that film, X-ray film to your doctor, and he will identify that where you have got some fracture, and he'll suggest you the treatment, further treatment, what he has to give you. So similar fashion, you have to study the structure of crystal, like how you have studied the structure of your hand. Similarly, you want to study the structure of a crystal. So similarly, what you'll do here, you'll pass X-rays through that, or else you'll pass electron beams. You can pass electron beams, or you can pass X-rays, or you can pass neutron beams. So any type of these these three things you can make, and the spectrum obtained after passing through this crystal is analyzed, and hence therefore we can determine the structure of the crystal. So it's very interesting one, and this type of science is called crystallography. Okay, it's called crystallography. So determining the structure of crystal using various methods we have. So we'll do it in next classes, and further when we enter into the real topic, you will understand how do we determine the structure of crystals. So now let me go into the next basic differences between amorphous materials and crystalline materials. So let us see what are the major differences we have. See, in crystalline materials, I have already told you that they are regularly arranged. Either the atoms or molecules are regularly arranged. But in amorphous material, there is a random arrangement, or it's a random arrangement or irregular arrangement we have in amorphous materials. This is the first major difference we have. Now coming to the second major difference, crystalline materials are anisotropic while amorphous materials are isotropic. Here I have written here, see, I'll be pointing you here. They are isotropic and here they are anisotropic. What is the difference? See, if I take a thermal conductivity, a basic property of a material, if I take this property, so it changes in different directions. This thermal conductivity is not constant in all the directions here in a crystalline substance. It changes in different directions, but here within the material. But here when I come to isotropic substance, here in all directions, the thermal conductivity is constant. So that means it is an isotropic material. The amorphous material is isotropic material, while crystalline substance is an anisotropic one. Now let me go to the cooling curve. See here, the cooling curve has breaks here in a crystalline material because of the process of crystallization. But here the cooling curve is always smooth. Cooling curve is always smooth. But here we have breaks in between. So why do we have breaks here in a crystal? Because while we are cooling the substance material, it slowly becomes into crystallized material. So during the process of crystallization, what happens? There will be breaks in between because some atoms will come together and the alignment will be changing rapidly. But here in amorphous material, the cooling curve is always smooth. You have to remember this. This is the third major difference between amorphous and crystalline material. Now coming to the bonds. Here all the bonds are equally strong in between any two atoms because of the symmetry. The major thing is symmetry. Symmetry means regular arrangement of atoms. They are symmetrical at any in any direction we observe. But here the bonds are not equally strong here in an amorphous material. So this is the fourth major difference. These four major differences you have to point out when in any examination they gives you for any short answer. You have to just make it a point to write all these 4 points in your examination. Now, next comes space lattice. So what is a space lattice? So I think you have heard this term in your intermediate, I think so. But let us see in deep now. So what is this? So we all know that a crystal is a three-dimensional body. The crystal is a three-dimensional body. Then the periodic arrangement of atoms in a crystal is called lattice. You already studied now. An array of points in space such that the environment about each point is same. See here. Now, if you consider this point here in the figure 2, if I consider this point, so the environment is same from each point. Like this is at equidistant from this atom, and this atom, and there will be one more atom here upward. I didn't draw. So if it is the environment of this atom is same when we observe from either of these 4 points, and it's a three-dimensional, so there will be other point back of this and front of this. So from these 6 atoms, the atom here seems to be in the same position. So that means the environment about each point is same. So hence this is termed as space lattice. An array of points in space such that the environment about each point is same is called space lattice. The points in space are termed as what? Lattice points. So each point in these lattice, space lattice, are termed as lattice points. All these are called lattice points. The lines joining these lattice points, see here, the lines, dotted lines here, the lines joining each of these lattice points are called lattice lines. Lattice lines. Similarly, a plane containing these lattice lines. So these lattice lines are in a plane. So when these are in plane, all the lines which are arranged in a plane. So these planes are called lattice planes. So in space lattice, we have lattice points, lattice planes, and lattice lines. Okay. So all these are shown in this figure 2. Now also I want to point out here this vectors A bar and B bar. See here. So when I consider two vectors A bar and B bar here, that is the line joining A and B, that is two lattice points here in this direction, in horizontal direction, that vector is termed as A bar. In the vertical direction, a line joining between the two lattice points, that is termed as B bar. So these are called translational vectors. Okay. Now let us learn what is a basis and what is crystal structure. Okay. Now we already studied what is lattice. Now I think all of you know what is space lattice now. Now let us see what is basis first. So what is basis? A set of one or more atoms about the lattice point, remember, is called basis. See now here I am showing here space lattice in figure A. This is space lattice. So space lattice consists of lattice points, and these line joining these lattice points are called lattice lines, and the plane consisting of lattice lines is called lattice plane, the entire plane. Now you see, if I put two atoms here, this is one atom and this is one atom. So a set of two atoms here, that is a basis now. I'll put the set of two atoms at each and every lattice point. Now I'll arrange in that fashion. So then this is called crystal structure. This is called crystal structure. That means at each and every lattice point, I put some basis. A basis means which is either a single atom or more than one atom. And moreover, the atoms may be of same element or different element also. So that type of combination is said to be basis. So when a basis is kept at each of the lattice points, then we consider that the entire structure is called crystal structure. So lattice plus basis gives you the crystal structure. Okay, so it is as shown here, right? So lattice plus basis gives you the crystal structure. Now let us see what is unit cell. What is unit cell? See the meaning itself, it says unit, a small single cell, unit cell, one cell, unit cell. What does that mean? The smallest geometrical figure obtained by the repetition of this smallest geometrical figure, which gives the actual crystal structure, is called unit cell. See, when this unit cell is repeatedly added in all the three directions, then we get the main crystal structure. So that smallest geometrical figure which we can obtain from a crystal is said to be unit cell. So it is also defined as, so it is having one more definition. Let me teach you that also. It is also defined as the volume of a solid from which the entire crystal may be constructed by translational repetition in 3 dimensions. What I told you now. So it has to be repeated in, see here, I am showing this crystal here. See, this is X direction, this is Y direction, and this is Z direction. So now I want to repeat the same crystal in this direction. So I want to add one more crystal here, one more unit cell here. So that gives you, in X direction, if I'm going to add up, pile up the same type of unit cell repeatedly, if I add on in the X direction, similarly, I want to add on in Y direction. This is Z direction. And now I want to add on in the Y direction this way. Now what happens? I'll form a entire crystal lattice, entire crystal structure by each of these unit cells. So each of these unit cells, when they are seriously arranged in 3 dimensions, that is X dimension, Y dimension, and Z dimension, translational repetition, you shall have to remember. There is no rotational motion, only translationally they were just attached to each other. That means parallel, they were added up. So that type of in the same direction. So that is called entire crystal structure is formed. That small amount of volume, the small geometrical figure, the smallest possible geometrical figure is termed as unit cell. Now let me see the figure here. See here I'll explain you what is this. So what the figure shows unit cell, the figure shows a unit cell here with, the figure shows a unit cell. Okay, here with what? Here we have edges like OX is A bar vectors, OY is OY or OC is in which direction? This is B bar, and OZ or OA is C bar. Okay, and what are the angles between these two? Well, let us see now. So between X and Y axis, the angle is gamma, while angle between Y and Z axis is alpha, while that of X and Z axis is beta. So you have to easily remember, you can easily remember alpha, beta, gamma. So gamma is similar to, is related to Z axis if you suppose. So the opposite direction you have to put gamma, like this direction you have Z here, see here. So you can put this as gamma between A bar and B bar. While coming to B bar and C bar, you can put alpha. For C bar and A bar, we have put beta, where O is the center, origin of these vectors in translational direction. So this comprises our unit cell. Okay, this comprises our units alpha, beta, and gamma, the angles between B and C, C and A and B respectively. Okay, so this is our unit cell here. Okay, right? So the smallest geometrical figure which is formed with which repeating itself in translational way in all the 3 directions, we obtain the entire crystal system. Such type of thing is called unit cell. Now next, what is a crystal lattice? Let me explain you what is a crystal lattice. The entire lattice structure of crystal, the entire lattice structure of crystal is found to made up of what? Identical blocks or unit cell. Okay, the lattice is known as, such type of lattice is known as what? Crystal lattice. What I have told you all previously, like the crystal lattice which is formed by repetitive translational repetition of all the unit cells in 3 different directions. That gives you crystal lattice. That gives you crystal lattice. Now coming to the lattice parameters of unit cell. So we have a unit cell. Now I want to have determine the parameters of unit cell. As I told you in the previous slide, the distance between two neighboring points is called the edges of the unit cell. As I told you, distance between this, if this is a lattice point at O and I have a lattice point at E. Okay. So now the distance between these two is called edge, EDGE, edge. And then now the length OA bar and OB bar and OC along these OX, OY and OZ, okay, are called what? Axial lengths or intercepts. What are they called? Axial lengths or intercepts. So the angles between these three intercepts, alpha, beta and gamma, are called interfacial angles. So what all these angles are called? Interfacial angles. See here, what is facial? I just want to tell you. What is face? F-A-C-E. What is a face? See, in a cube, how many faces we have? 6 faces we have. For a cube, we have 6 faces. So, interfaces. So, between the faces, between any two faces, what is the angle? What are the angles we have? Alpha, beta and gamma. So, they are called interfacial angles. So, between the 3 intercepts. What are the intercepts here? OA, OB and OC. They are called A bar, B bar and C bar, as we have discussed in the previous slide. So A bar, B bar and C bar. So these are called interfacial angles. So let me come and revise you again. So basically the solids are classified into 2 types. They are amorphous and crystallines. First of all, the materials are classified into 3 types: solids, liquids and gases. So matter is composed of atoms and molecules, and the arrangement determines the state of the system. Like now solids are classified into amorphous and crystalline. Crystalline substances are having regular arrangement, while amorphous are irregularly arranged. So crystal definition I have told you, and crystallography we have discussed. And again, the major differences between crystalline and amorphous materials also we have learned. And now what is the space lattice? We have determined the lattice point, the lattice line and lattice plane. And then we have come to basis and crystal structure. So a crystal structure is nothing but lattice plus basis. So then we have determined the unit cell. So the smallest geometrical figure which is formed and by repeatedly adding it up in translational directions in 3 directions like x, y and z, we obtain what? We obtain the entire crystal system. So such type of smallest possible geometrical figure is called unit cell. So when I consider a unit cell, here we have alpha, beta and gamma are the interfacial angles, while A, B and C are the translational vectors along x direction, y direction and z direction respectively. These interfacial angles and axial lengths or intercepts are called lattice parameters. They are called lattice parameters. Okay. So now you have got a brief idea of what are crystals and what are amorphous materials, and how in the crystal, how we can determine the type of crystal structure by 2 parameters. They are lattice parameters. One is axial lengths or intercepts and other one is interfacial angles. So relation between these intercepts like A, B and C and relation between these interfacial angles alpha, beta and gamma gives you different types of crystals, different types of crystal systems we can have. So later, how can we determine the crystal structures? By crystallography, like various methods we have to determine the crystal structures of various crystalline materials formed by various synthesis methods. For example, sodium chloride, that is a common salt we have every day in your food. So what is common salt? It is NaCl, sodium chloride. So it is formed by sodium atoms and chlorine atoms. There's sodium ions and chlorine ions. So how do we determine the arrangement of, how do we understand the structure of bonding between sodium and chlorine to determine the structure of sodium chloride crystals. So this may be a good example for us to learn in, in making it as a generalized example to all of us. So let us learn the various crystal structures based on the relations between intercepts and axial lengths, or else interfacial angles also in the next class. So thank you students for being with me and having a patient listening. Thank you all.